Hey, I wanted to finish the section 2.1 notes with you. So we've already finished the first 2 pages. So let's take a look at the next page, which is starting with example 4. So what we've done up to this point is we've just found the derivative of functions or the slope of the tangent line at a specific point using the limit definition. So we're going to continue to do that before we start talking about shortcuts. So find f prime, again, that's what that little kind of apostrophe looking thing, that's how we read that, f prime, or the derivative of f for the function square root of x. Then find the slope of the graph of f at the points 1, 1 and 4, 2, and discuss the behavior of f at 0, 0. So again, when we say find the slope of the graph of f, we're really saying find the slope of the tangent line to the graph at these 2 points. Okay, so again, by definition here, we've got f prime of x is equal to the limit of f of x plus h minus f of x over h, all as h is approaching 0. All right, so then for our specific function, we're asked to find the limit. And here's our function, so we're going to say the square root of x plus h minus f of x, which is just square root of x all over h. Okay, this goes back to our work in the last chapter where we're trying to figure out how to take the limit with a radical in it, and our strategy there was to just multiply numerator and denominator by the conjugate of the numerator. So in this case, we're going to take this right here and multiply it by square root of x plus h plus square root of x all over h. Okay, so when we do that, then let's multiply that out, and we get the limit as h approaches 0. This is just going to give us an x plus h. Then when we get square root of x plus h times positive square root of x, that's going to give us the positive version of that. When we multiply these inner terms, we're going to get the negative version of that, so they're just going to cancel out. And then finally, when we do the last terms, we're going to get minus x. And, oops, well, typo here. This should be over square root of x plus h plus square root of x. Sorry about that. So in the denominator, then, we're going to come over here and we're going to say h times, and again, as I've suggested to you before, don't distribute that h out. Our whole goal is to cancel that because that's the troublemaker. That's where we've got it. That's where we get the 0 in the denominator. So just leave this square root of x plus h plus square root of x. All right. Then we're going to simplify up here. Again, we always said that this latter part should cancel out with something prior to it, and there it does. So we're just left with limit as h approaches 0 of h over h times the square root of x plus h plus square root of x. All right, these cancel. So we just have 1 over square root of x plus h plus square root of x. We let h go to 0. So this is just going to become square root of x. This is going to stay square root of x, so we end up with the derivative function being 1 over 2 times the square root of x. All right. Again, just from a domain perspective, remember that we can't put any negatives under the radicals, so x has to be greater than 0, but we also can't put any 0, or we can't let the denominator of a function be 0. So here we're going to say that x must be strictly greater than 0. All right, so again, if this square root were in the numerator, we would say greater than or equal to 0, but since it's in the denominator, we have to say greater than 0. All right, so then this is what we would call f prime of x. All right. And then it asks us to do 2 things. Find the slope of the graph of f at the points 1, 1, and 2, 4. So let's do 1, 1. So at 1, 1, the slope of the tangent line to the function is, and then we're just going to plug 1, this one right here, because it's the x value. We're going to just plug it into the function, so we get 1 over 2 times the square root of 1, which is just 1/2. So the slope of the tangent line at that point is 1/2. And then we do the same thing for the point 4,2. So at 4,2, the slope of the tangent line of the function, blah, blah, blah. Eventually, we're just going to start just saying the slope, even though we mean the slope of the tangent line. The slope of the tangent line is, and again, we plug 4 into for x here, so we get 1 over 2 times the square root of 4, which ends up giving us 1/4. Right, and again, we would say that this right here is f prime of 4. We just plugged 4 into our function right here, and we ended up with 1/4. And again, same thing, we would say that this was f prime of 1. We just take that derivative function and we plug the x value in. So we say it's f prime of 1, but the way we interpret it is it's the slope of the tangent line to the function at that point. Okay, 2 other things. One, it says discuss the behavior of the function at 0, 0. And again, this is with regards to the slope, so we're going to take this f prime of 0, all right, and we're going to plug 0 in here. So we end up with 1 over 2 times the square root of 0, and we get 1 over 0, which is undefined. So slope is undefined. And what we would say is, think about that. When we're talking about a line, just a regular line whose slope is undefined, remember that means that it's a vertical line right there, all right? And so what that would mean is that there's a vertical tangent line. At 0, 0. All right, let's do a quick sketch here. I didn't leave a whole lot of room to do this, but let's look at what square root of x looks like and then why we would possibly get a vertical tangent line. So I'm going to do 1, 2, 3, 4, and then we'll just do 1, 2. All right, so for square root of x, again, our original function, at 0, it's 0, at 1, it's 1, and at 4, it's 2. All right, so we end up with something that looks like this. All right, so if we were to draw the tangent line at 1, we would get something that looks like this. All right, so we're saying there that the slope is 1/2. Here, as we go farther to the right, as our x values increase, the slope decreases. It kind of flattens out here, and so we're saying at this point, the slope of the tangent line at the point 4,2 would be 1/4. But then here, as we approach 0, what's happening is our slope, it's this part of the graph is very steep. And it's steepest as we approach 0. And in fact, if we were to draw a tangent line there, it would end up being completely vertical right there. Again, this square root is basically half of a parabola. But we just don't put the bottom half in because then it would not be a function. But again, what's happening here is it's that curvature of a parabola. And so right there we would say that the slope of the tangent line, if this were a parabola, again, let me turn this like this. If it were a parabola, we would say, oh yeah, the slope of the tangent line there is 0. So when we put it in this correct position for square root of x, we would say, oh no, now it's vertical. And so we would say there's a vertical tangent line there. The slope is undefined. Okay, for example 5. Find the derivative with respect to t for the function y equals 2 over t. So here, again, in our original one that we did in example 3, it was just a factor and cancel. In our second one here, example 4, we're looking at square roots. And again, the third type of limit process that we talked about was with complex fractions. So we want to see how that's going to look here. All right, so because we've used y here, I'm going to call that y prime. And we would just say that that's the limit as h approaches 0 of f of, well, it's a little bit weird to say f of x when we're talking about y, but again, remember that they mean the same thing. So f of x plus h minus f of x all over h. So that's just the definition, and specific to our function, we're going to say that that's the limit as h approaches 0 of 2 over, we're going to replace, well, I guess here we should go back and call this t, sorry. Okay, so in this case we're going to call it 2 over t plus h minus 2 over t all over h. All right, so again, I just replace t with t plus h in this first part of the numerator, and then I just leave it alone in the second part. All right, so if you think back to what we did with functions like this, our strategy was to get rid of the complex fractions. And the way we did that was we multiplied numerator and denominator by the LCD of all the fractions. Again, I'm just going to stick a little 1 in here for right now, so you see that these are the 3 denominators. So that LCD has to include a t plus h, and it also has to include a t. Right? So we're going to say it's t plus h times t. Again, it doesn't matter if you put the t in front. In fact, that would probably look a little bit better. I'm going to make this a fraction, again, just so visually we're not confused about what to multiply it by. They all look like fractions, so you know you should do it to the numerator. Down in the denominator now, I'm just going to get rid of that 1. And since this is not a fraction, I'm just going to write it as t plus h times t. All right, so we're taking that and multiplying it by this. All right, when we do that, again, the whole purpose of doing this is to get rid of those denominators. So when I multiply this first fraction, when I distribute this to the first fraction, those t plus h's cancel out. So all that's left is 2t. So limit as h approaches 0 of 2t. And then when I repeat the process here, the t's cancel out, but not the t plus h. So we end up with minus 2 times t plus h all over. Again, don't distribute. We've got h times t plus h times t. Okay? All right, let's simplify more. So I'm going to distribute in the top. So I end up with limit as h approaches 0 of 2t minus 2t minus 2h all over h times t plus h times t. All right, these are going to cancel. And I end up with limit as h approaches 0 of negative 2h all over h times t plus h times t. All right, now's the time to cancel out our h's. Again, h is the offending thing here, so we're trying to get rid of it in the denominator. So we end up with limit as h approaches 0 of negative 2 over t plus h times t. All right, we still have an h in here. Again, that's why we still have the limit. We can't get rid of that until we actually take the limit, until we actually plug 0 in for h. All right, and when we do that, we end up with negative 2 in the numerator. In the denominator, this h goes away, and so we just are left with t here. So t times t gives us t squared. All right, and again, that's y prime, or the derivative function for the original function of 2 over t. Okay, so in our last example, it asked us to find the slope of the tangent at specific points. It doesn't ask us to do this, it's just saying to find the derivative, so we're done here. For some reason down here I have said that I do want to look at a point, so at the point one, two, and again, let's just make sure that that is a legit point. If I plug 1 in here for t, I do get 2, because 2 over 1 would be 2. All right, so that is a legit point. So at the point 1, 2, the derivative, again, I'm going to write f prime just so that we can see the 1 in there. That's maybe a weakness of the y prime notation, is that we don't get to keep track of the x value that we used, but we end up getting f prime, we end up getting negative 2 over 1 squared, which would give us negative 2. All right, and so then I'm also finding the tangent line. It's possible that when I typed this up, I forgot to ask to do that, and so I'm just doing it right now. All right, so then we would say the tangent line at 1, 2 is, so remember we talked about these before. We would do y minus y1 equals m times x minus x1. And so we're going to say y minus 2 equals m, again our negative 2, x minus x1, which is just 1. So we would get y minus 2 equals negative 2x plus 2. Bring the 2 over, y equals negative 2x plus 4. So that would be the equation of the tangent line. All right, so this function, 2 over t, and again, this has the two parts to it, because as t is positive, well, let's just draw it. I was going to say I'll only draw half of it, but let's just do both. All right, so we've got 1, 2, 3, 4. All right, when x is, well, let me just finish this. All right, we've got negative 4 here, negative 2. Okay, so when at t is 1, 2 over 1 is 2, so we've got up here, when t is 2, 2 over 2 is 1. When we've got 4, 2 over 4 is a half. And if we did a half right here, we would end up at 4. All right, so on this side, it looks like this. And on the other side, it looks exactly the same. I'm going to skip that just for the sake of drawing what I would like us to draw, which is I want you to see what the tangent line looks like at that point 1, 2. All right, so here's the point 1, 2. It tells us that our tangent line has the equation negative 2x plus 4. So again, what that means is going to cross up here at 4, and then it's going to have a slope of negative 2. So down 1 over 2. In fact, we just touched that point that we're talking about, 1, 2. So we've got that point, down 1 over 2. And so we end up with our tangent line looking exactly like this. Well, as best as I can draw as a human. All right, and so we see our tangent line to the graph of 2 over t at that point, 2, 4. Okay? All right, next page. So at this page, we're going to look at this idea of functions that might be continuous but not differentiable. All right, so we've talked about continuity. Again, that idea is things that we can draw without picking our pencil up. We talked about the problems that come along with that, holes, jumps, or maybe a function not being defined as the limit at a certain point. All right, so situations where we had a hole and then the function was defined in a different way. So the limit did exist, but the function didn't match that, or the value of the function didn't match that. So we know what continuity is, but now we want to relate that to differentiability. So far the only 3 examples that we've looked at together, the function has been differentiable. Right? So what does that mean to not be differentiable? And essentially, if the definition of the derivative that we've been using for, since that involves a limit, it would not be differentiable if that limit doesn't exist. All right, so that limit that we've talked about, limit as h approaches 0 of f of x plus h minus f of x all over h. If that limit, which defines what the derivative is, if that limit doesn't exist, then we would say the function is not differentiable. So then the question arises, like, what do we do if we can't find, like, how can we prove that something is not differentiable, right? And so we have this alternative limit form of the derivative that's useful in investigating the relationship between differentiability and continuity. And so what we're saying here is the derivative of the function f at a specific point C. Again, remember ours was f prime of x, so we were talking in general. Here we're saying specifically, is it possible that it's just not differentiable at a specific point here? So the derivative of the function f at the point C is the limit as x approaches c of f of x minus f of c all over x minus c. Again, you should see the slope here. All right, when we look at that, this is our y2 minus y1 over x2 minus x1. But we're specifically looking at a certain value for that x1, all right? So the derivative of that function at c is this, provided the limit exists. And so then it says, note that the existence of the limit in this alternative form requires that one-sided limits must exist and be equal. Again, so maybe a derivative, maybe something's not differentiable, maybe a function's not differentiable because the one-sided limits don't exist or they are not equal. We've seen that in certain functions before where the derivatives are not equal. These one-sided limits are called the derivatives from the left and from the right, respectively. It follows that f is differentiable on the closed interval ab if it is differentiable on the open interval ab, and if the derivative from the right at a and the derivative from the left at b both exist. All right, we've talked about this also before when we talked about continuity on a closed interval. So here we're saying the same thing, that if we're talking about a closed interval, we can do that, and we extend the definition by making sure that as we approach a from values greater than it, all right, so here's ab. So as we approach a from values greater than it, the derivative exists, and then as we approach b from values less than it, the derivative exists. All right, a function that is not continuous at c cannot be differentiable. Right, so if we don't have continuity, it's not going to be differentiable. Right, continuity does not guarantee differentiability, but not continuity or not continuous does guarantee that it will not be differentiable. Right, and in fact, on the next page, we're going to talk about the strength of differentiability, about what that implies about continuity. Okay, so really, you might be thinking, oh, great, something else I have to memorize, like when do I even use that? So really, I mean, you can use it whenever, but really, the two times that we're going to run into functions where they're not differentiable, most of them will end up being absolute value functions, or functions that have fractional numerator or fractional exponents that are less than 1, or I should say whose absolute value, no, that are between 0 and 1, all right? So things like this, x to the 1/3, we're going to find that it's not differentiable everywhere. Here at absolute value, we're going to find it's not differentiable everywhere, and we're going to do that by using this new definition for the derivative. Okay, so let's take a look at example 6. All right, consider the function f of x equals x minus 2. That's so vague. What do they mean when they say consider the function? They're just kind of asking us to explore, but we're going to explore with some purpose here. Again, if you remember when we talked about absolute values, actually I'm not sure that we were talking specifically about this. We were mostly looking at the one where it was f of x equals absolute value of x minus 2 over x minus 2. If you remember that, in fact, I think we just did one of those in class too. So slightly different. What we see when we've got absolute value of x minus 2, again, that minus 2 means the vertex moves over to 2. And then we've just got our standard absolute value function. So rise over run, And it's going to end up looking like this on the right side of it, and then we would do the same thing, rise over run, with a slope of 1, but now it's -1 going in that opposite direction, and so it looks like that. Again, if we were to talk about the slope of each of these two branches, we would say, oh, here it's very clearly -1 this entire time. It's basically linear, all right? If we ignore the other half of that, that is a linear function right there. And so then we would say it's a constant -1. But then we consider the other branch, and we would say, no, the slope of this is +1, right? There is no opportunity for them to do like a gradual change from -1 to +1. It is very, very distinct. This is all -1, has a slope of -1. This all is +1. And so there's no opportunity to make this transfer from -1 to +1 a smooth one, right? And so we're going to see when we graph the derivative, when we take the derivative, that there is a very sharp turn. Wow, why did I do that right here? I meant to do it on this spot. So sorry if you graphed it right there. You can just graph it right in this spot. So at 2, 4, 2, 4, and we end up with just what I drew, but in the wrong spot. All right, so it looks like this. All right, let's pretend I didn't draw that. Okay, so let's use our new definition of the limit. All right, so we've got limit as x approaches 2, and we're going to do this one from each side. So as x approaches 2 from the left, we're going to see what happens here, and then we'll do it again from the right, just so that we can see we do not get the same slope as we're approaching 2, because it is going to differ there. All right, so the limit of x as x approaches 2 of f of x minus f of 2 all over x minus 2. All right, so we're just putting in that value 2. This is kind of like that c value that well, it is the c value, but again, remember when we were talking originally about our the very beginning of our discussion about derivatives, we talked about derivative at a specific point, not the derivative function. So this is kind of what we're doing here, at a specific point. Okay, so then let's fill in for our specific function here. So we've got limit as x approaches 2 from the left of f of x. Again, that means absolute value of x minus 2 minus f of 2, which is 2 minus 2 is 0. Absolute value of 0 is 0. And then over x minus 2. All right. So then this should bring back recollections of exactly what we were just talking about. Limit as x approaches 2 from the left of absolute value of x minus 2 over x minus 2. Again, we've discussed this a number of times in class, but let me just say it one more time just so that you remember. Because absolute value is just about the sign of, about making sure that whatever is in here is not negative, that it's positive or 0. We can consider two things. If x is greater than 2, remember that absolute value of x minus 2 is just whatever was in there, x minus 2. Absolute value of a positive number doesn't change it. Absolute value of 0 doesn't change it. And so then we can say that we end up with, in the numerator, x minus 2, and in the denominator, x minus 2. That is just 1. So the limit here is just, well, actually, sorry. Yeah, if x is less than 2, I should have done this as an aside, because this is actually what we need for the next one. So we'll actually have it when we go to do from the positive side. And as x is less than 2, we would say absolute value of x minus 2. Since 2 is, we're picking values less than 2, when we plug it in here, we're going to get a negative. And so the absolute value of it is going to change to the opposite sign. So this is going to be the opposite of x minus 2. And when we do that, opposite of x minus 2 over x minus 2, this is going to be negative 1. All right, so I'm going to put this not as a branch from here, but as an aside. And then we'll say, oh, since we're coming from values less than 2, this limit must be -1. So this is an aside. Just as a reminder about how we took the limit when we did these. All right, now as we take the limit as x approaches 2 from the right of absolute value of x minus 2 over x minus 2, we're going to say, oh yeah, we know that that's 1. All right, so we're going to see the limits don't match up. All right, the limits there of our derivative function don't match up. So we'll say, since the one-sided limits are not equal, f is not differentiable. At x equals 2. And what that means is the graph won't have a tangent line there. Okay, I can never tell if I'm going completely off screen because I'm sitting as I'm doing this and my viewfinder is out of range. So anyway, I'll just stop there just in case I went out of the screen for a while and you need to copy anything down. Okay, so let's take a look at this one. Consider the function f of x equals x to the 1/3. Again, this is cube root of x. All right, and so what we know is, let me make this 1, 2. I'm going to go up big for 1 here. -1, -2. I'll go down big for -1. At 0, it's 0. At 1, it's 1. And at -1, it's -1. All right, again, while that looks linear, we know that that's not what it is. It's just going to look like this. All right. And so let's use this limit definition, the new limit definition. Again, why am I using the new one? Well, because I know personally, and the textbook's author knows personally, that this is another one of those functions where we've got a problem here. Because here, again, the steepness here is such that we are going to end up with a vertical tangent line. Again, mine's probably not drawn very well. It's actually maybe a little bit more like that. All right, so maybe less of what I had and more like that. Again, so we see there that as we get to that tangent line, it's definitely becoming very vertical looking. All right, and so we're going to show, in fact, that it actually is completely vertical. All right, so again, I'm going to start with the limit as x approaches 0, because again, here the problem point appears to be 0. For this one we did 2 because the problem point is at that sharp turn. All right. And again, with practice you'll get better at this, but for right now I'm just going to pick those values and we'll discuss them. All right, so again, it's f of x minus f of 0 over x minus 0. And now I'm going to put in the specific function for f of x and the specific value of the function at 0. So we're going to get x to the 1/3 minus, and we plug 0 in here, f of 0, we end up with 0 all over x minus 0. Sorry, I forgot my limit here. Limit as x approaches 0. If we continue on with this and simplify, we get limit as x approaches 0 of x to the 1/3 over x. Right? And then again, this simplifies into limit as x approaches 0 of 1 over x to the 2/3. All right, so then as we try to substitute 0 in for x, we know we end up with 1 over 0. And so we know that anything that is of that form has a vertical asymptote there, and what the function is doing is it's going to infinity. All right, so we're going to say that this is infinite. And then let's talk about whether it's positive or negative infinity. It is positive infinity, but let's see why that happens. As I choose values greater than 0 that are close to 0, so let's say 0.5, again, what is this saying to us? It's saying we take the cube root of it and then we square it. So when that x value is positive, we take the cube root of a positive number, that's positive, we square it, it's positive. What happens when we choose an x value that's negative? So let's say negative 0.5. Well, we put that in, we are allowed to take the cube root of a negative number, so cube root of negative 0.5 does exist and it is negative, but then we square it and it becomes positive. So in either case, it's not that it's going to change from one side to the next, that it will be positive infinity in both directions. Either way, it's infinite, therefore it is, it's just, that means the tangent line right there is vertical, right? So we're going to say, since the limit is infinite, the tangent line at 0, 0 is vertical. So f is not differentiable. I'm just going to say DIFF for differentiable at x equals 0. All right. Again, hoping I got that whole thing in there for you. Okay, last page. So here we have theorem 2.1. If f is differentiable at c, then f is also continuous at c. So I'm going to remind you back in the middle of the previous page where we had this line here. If f is not continuous at x equals c, then it is not differentiable at x equals c. But here we're going to get the stronger positive version of this, which says if it is differentiable, then it is also continuous. In other words, differentiability is stronger than continuity, right? If you're differentiable, then you're differentiable, but it also guarantees continuity. Continuity does not guarantee differentiability. All right, so maybe we could say here differentiability sorry, I can't write and spell it at the same time. B-I-L-I-T-Y. Differentiability is stronger than continuity. All right, so let's look at these relationships here. The following statements summarize the relationship between continuity and differentiability. If a function is differentiable at x equals c, then it is continuous at x equals c, so differentiability implies continuity. However, it is possible for a function to be continuous at c and not be differentiable at c. Therefore, continuity does not imply differentiability. Again, we just saw two examples where the function was continuous at c, but it was not differentiable. And again, those two examples right here. This absolute value of x minus 2 is continuous at 2, but it is not differentiable there, right? And that occurred because we had that sharp turn that did not allow for a gradual change in the slope. It was a very, very distinct, sharp change. Right? And then the second example here was when we had a function that had a fractional exponent where that exponent was between 0 and 1. And what we found was that we ended up with a vertical tangent line, and so it's not differentiable there. All right. And so I'm just going to summarize here and say those two examples because, truth be told, those are the ones that we're going to see most often. So we will say a function will not be differentiable at a point at which its graph has a sharp turn, all right, and again, I'm just going to point out that this most often happens with absolute value, so often absolute values. All right, so a function will not be differentiable at a point at which its graph has a sharp turn, so absolute values, or a vertical tangent. And again, that is often a function with a fractional exponent. And again, it's usually when that exponent is between 0 and 1. And again, when we learn the shortcut, you're going to understand that more, between 0 and 1. Or a radical, and again, remember that shouldn't be a surprise because radicals are fractional exponents. So you might see it with the fractional exponent like we just saw in the x to the 1/3, or maybe it's going to be written as cube root of x, and you're going to need to remember, oh yeah, that's a fractional exponent, so that falls into that category. Right, so again, when we run into a function that's not differentiable, or if we're wondering if a function is not going to be differentiable, two things that should set your spidey senses off are, does it have an absolute value in it, and does it have a vertical tangent line? Now, let me just say one more thing. If I looked at this and I was asking, is this function differentiable at 4? Well, yeah, that's not the problem spot, all right? So again, don't be tricked into thinking this is going to be not differentiable everywhere. It's just at that specific point, all right, where that sharp turn takes place. And again, if I was asked, is f down here differentiable at 2? Yeah, it is. This is the problem spot. So we don't want to lump the whole thing into saying that it's not differentiable anywhere. It's just that there will be problem spots, and those problem spots are going to occur where there's a sharp turn, sharp point, or a vertical tangent. Okay, let me know if you have any questions. Bye.